Bismillahirrahmanirrahim. As you know, we are discussing, in fact, the D and F block elements. In the previous lecture, we discussed its various factors. Today, we will continue to describe the electronic configuration of 4D and 5D transition elements. Now, as we have discussed the different transition elements involve the process of completion of electron in D and F orbitals. Transition elements involve the process of completion of electron in D or F orbital, or D and F orbital are partially filled Now we consider the different series in the form of a table, that is 3D block elements, that is the element, and here electronic configuration, then 4D block elements, that is the element and electronic configuration, then 5D block elements, here element and electronic configuration. Now here the electronic configuration, we can divide these in the column. Now the 3D, that is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, and finally the zinc. That is 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30. Now this is the 3D block elements. Their electronic configuration can be described as argon with 3D1 4s2. This is 3D2 4s2. This is 3D3 4s2, that is the vanadium. Then the chromium 3D5 4s1. Now these are the, similarly you can write for others, that is 3D5 4s2, 3D6 4s2, 3D7 4s2, 3D8 4s2, 3D10 4s1, 3D10 4s2. This is the first transition series. Now we come to the other, that is yttrium, zirconium. These are the elements which are included in this series. This is molybdenum. These are the rhodium, ruthenium, that is palladium, silver, cadmium. This is 39, 40 up to 48, 41, 42, 43, 44, 45, 46, and 47. Again, here we can also write the electronic configuration: krypton 4D1 5s2. This is similarly 4D2 5s2, 4D4 5s1, and similarly in this case you can write up to the last, that is 4D10 5s2. And similarly here you can also write. Here 4d5, 5s1, and similarly you can also write these 4d6, 5s1, 4d5, 5s2, 4d7, 5s1, 4d8, 5s1, 4d10, 5s0, 4d10, 5s1. Now these electronic configurations, they are basically based on two factors. For the stability of the transition metals, the transition metals are the compound, they become stable when the transition elements, they possess either the complete d orbital d10 or it has about half filled, that is d5. So they become stable. Now in this case, that is lanthanum, it is 57, then hafnium 72. These are the different elements, that is the tungsten, osmium, iridium, then platinum, then gold, and finally mercury. Now this is 73, 74, 75, 76, 77, 78, 79. Now similarly we can write the electronic configuration here as well, that is xenon 5d1, 6s2, 5d2, 6s2, 5d1, 6s2, and here if you have the f orbital as well, so you can also write here 4d3, 6s2, 5d5, 6s1. The last, that is xe 5d10, 4f14. Now here d6, d7, d8, you can similarly write all this. Now this is 5d5, 6s2, 5d6, 6s2, 5d7, 6s2. Now here in this case 5d9, 6s1, 5d10, 6s1. Now this is basically the table describing the electronic configuration or electronic, you can say this is a distribution as well, that is the electronic distribution of 4D and 5D transition elements. Now if you see that if we compare this, that is the chromium. Now here the extra stability is gained by this due to the half filled d orbital and half filled s orbital. And similarly if we consider this one, that is the copper, here again the extra stability has got this copper with the complete d orbital and half filled s orbital. The same case over here is, in this case, that this is basically half filled d orbital and here it is 5s1, this is half filled, and again here in this case that is 4d10, that is complete d orbital, and 5s1 which is half filled. And the tungsten, in this case the same is happening, that there is half filled d orbital with the half filled s orbital, and in this case as well, that is the 5d orbital, 5d10, this is complete, and here it is 6s1. Now basically the electronic distribution in these different series, that is 5, this is basically the 4D by comparison. Now especially in these two cases, the irregularities in the electronic distribution, they depends upon different factors as we have earlier discussed, that is the nucleus electron attraction, that is the interelectronic repulsion. Some other factor is the shielding of one electron by the other electrons, and lastly the energy exchange factors. These basically are very significant while considering the electronic distribution in the 4D and 5D transition element series. Now we will discuss the other very important properties and characteristics, that is the binding energies. The transition elements having higher binding energy possess the property of toughness, malleability and ductility, means that they are tough, malleable and ductile. Now the transition elements, in fact they have higher binding energy, possess the property of toughness, they are tough, malleability, that they are malleable, and ductility, that is the ductile. Now binding energy basically is due to the presence of the unpaired electrons. The binding energy increase from left to right of 3D transition elements due to increase unpaired up to the middle of the series. Now the binding energy that increases from left to right in the 3D series transition elements due to increase in the unpaired electron up to the middle of the series. Now the 3D elements, that is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc, that is 21 to 30. So if we move from left to right up to the middle, this increases. Now if we consider the electronic configuration, that is scandium 21 Ar 3D1 4s2. So the number of unpaired electron, they start increase from scandium up to the vanadium and chromium. The number of unpaired electrons, they increase from left to right, so binding energy increases. अब ये बाइंडिंग एनर्जी जितनी ज़्यादा होगी ज़ाहिर है उसमें टफनेट भी होगी, इनके मेल्टिंग बॉइलिंग पॉइंट्स भी इंक्रीज करेंगे. नाउ आफ्टर द फ्रॉम द मिडल टू द राइट, देन बाइंडिंग एनर्जी डिक्रीजेस ड्यू टू पेयरिंग ऑफ इलेक्ट्रॉन्स. लेकिन बाद में चूँकि इसमें पेयरिंग आ जाती है, लिहाजा फिर ये बाइंडिंग एनर्जी जो होती है वो डिक्रीज़ करना शुरू कर देती है. एंड इन केस ऑफ कॉपर 30, इट इज़ Ar 3D10 4s2. This is basically group 2B, no unpaired electron. So as we move towards right of the 3D series, the number of unpaired electron, they become 0. This can be shown in the your textbook in the graph, that how this increases up to that is from sodium, potassium, scandium, titanium, vanadium, it start increasing then after middle it start decreasing. So there is an irregular pattern. Now we come to another feature, that is variable oxidation state. Now oxidation state is in fact the number of, that is, it is the apparent charge, whether positive or negative, which an atom would have in a certain compound, that is called oxidation state. Since the transition elements are electropositive, these show positive oxidation state. Metal, they are usually electropositive, so they show the positive oxidation state. All 3D transition elements show an oxidation state of +2 in addition to higher oxidation state when use NS electrons in bonding. Now the NS means the 4s orbital. The transition elements show variable oxidation state due to having available n-1d and ns electrons. The n-1d and ns electrons have almost same energy. Therefore, the n-1d electrons can easily be utilized, can easily be lost. Now, the factor is that they show variable oxidation state because of availability of the S and NS electron. These have almost same energy, so they can be utilized for the variability or variable oxidation state. Now, almost same means that very close, their energy values are very close to each other. For example, manganese show +2 oxidation state, +3 up to +7 variable oxidation state. In higher oxidation state, the Nd and Ns electrons are utilized for bonding. That is the variable oxidation state. In general, +2 and +3 oxidation states are common. तो लिहाजा यहाँ पे हम ये बात कर रहे हैं कि बेसिकली जो ट्रांजिशन एलिमेंट्स हैं ये इलेक्ट्रोपॉजिटिव हैं और ये पॉजिटिव ऑक्सीडेशन स्टेट ही नॉर्मली शो करते हैं, और जो 3D ट्रांजिशन एलिमेंट्स हैं नॉर्मली इनमें +2 ऑक्सीडेशन स्टेट होती है इन एडिशन टू द हायर ऑक्सीडेशन स्टेट एज वी आर डिस्कसिंग. द ट्रांजिशन एलिमेंट्स शो वेरिएबल ऑक्सीडेशन ड्यू टू अवेलेबिलिटी of the NS and these electrons. These have almost very close energy, therefore they can be easily lost for the bond formation. For example, manganese show +2, +3 up to +7 variable oxidation state. In higher oxidation state, these electrons are utilized, whereas in general the +2 and +3 they are common. Now we can also explain by drawing their electron in the valence shell. Now the manganese basically, that is scandium, titanium, vanadium, chromium, manganese. Now the number of unpaired electrons, they vary. In this case, in case of especially the manganese, there are, this is 3d5 4s2. So when the d electrons and the s electron they are utilized, commonly the scandium, it has plus 2 plus 3, then plus 3 plus 4 plus 4 plus 5 plus 6, and here the oxidation state is shown plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. So if you come to from scandium to zinc, that is 21 to 30. So this sort of graph you can have. Here is the manganese, that is plus 2, plus 3, plus 4, plus 5, plus 6 and plus 7. Like this you have got, so maximum is the plus 7 in case of manganese. So plus 2 plus 3 plus 2 plus 3 plus 4 plus 3 plus 2 plus 3 plus 4 plus 5, then plus 2 plus 2 plus 3 plus 4 plus 5 plus 6, but here this is the maximum plus 2 plus 3 plus 4 up to plus 7. Then after manganese, that is iron, then it is plus 2 plus 3 plus 4 plus 5 plus 6, then there is a cobalt, then there is nickel, and then there is a copper. So the oxidation state normally increase from plus 2 to plus 7 up to the middle due to the increase in the number of unpaired electrons. So that's why it shows a variable oxidation state. The next aspect is catalytic activity. The transition metals and some compounds are used as catalyst due to their ability to show variable oxidation state. In this way, they can form intermediate, that is short-lived species intermediate product with various reactants. Now the important is that they have the ability to show oxidation state, and they form some intermediate which are short-lived and unstable, which automatically then are changed into the main product. For example, zinc oxide and iron oxide, chromium oxide are used as catalyst in the manufacture of or in the preparation of methyl alcohol. Similarly, nickel, palladium and platinum are used as catalyst for the hydrogenation of unsaturated hydrocarbons, preparation of vegetable ghee, etc. V2O5 as catalyst to convert to oxidize SO2 into SO3 to manufacture H2SO4. Iron is used as catalyst in the Haber process to prepare ammonia. So there are various catalysts which are usually utilized. For example, that is, they are used in the catalyst. Similarly, nickel, palladium, nickel is used by heating, and palladium and platinum they used similarly at room temperature. Then vanadium and then iron. There are so many other catalysts which are used as a catalyst. So in general you can say that the transition metals and their compounds, they are used as catalyst because of their ability to show variable oxidation state. They have some active sites which binds to the reactant to have the activated complex, which finally is converted into the products in the form of intermediate. So these are the different catalysts which are utilized. So till then then we inshallah discuss the other factors. Allah Hafiz. Assalamu alaikum.